We're going to continue on here. Chapter 13. We're talking about equilibrium. Obviously, we're talking about the equilibrium constant, which is our products over our reactants, essentially. And we do use the coefficients as the exponents for each of those. And as we talked about, the equilibrium constant is a constant value for a particular reaction. Based on a couple of factors, based on what it is, how the reaction is written, and also really the temperature. So as we talked about, again, it's really only the temperature that will affect the actual value of the equilibrium constant. And again, what we're talking about there is if we compared the K value at, say, two different temperatures, those guys would be different values for K. But if we did a bunch of different experiments all at the same temperature, we should get the same equilibrium constant. And as we talked about, it really doesn't matter how much you start with in different experiments. It will always come to sort of rest in terms of equilibrium at the same ratio of products to reactants, and you'll get the same value. So again, you don't always have to start with the same amount to get the same value of K. The only thing that will change is the temperature will change the value of K between the two values. But if you keep the temperature constant, it will stay constant. It is one of the few things in chemistry that's just a number. So when we do give the value of K, it is, again, just a number, but it does tell us several things. If we do see a large value of K, that means that when we reach equilibrium, we should mainly expect products to be formed. As just mathematically speaking, in order to get a large number, you need a big number on top there. Divided by a small number gives us a large value of K. Opposite is true. If we see a small value of K, it means when we reach equilibrium, we mainly have reactants that are present. And it's the same sort of mathematical approach. In that case, you would have much larger number there on the bottom than you do on top. And that will get you a smaller value. Remember that a large value of K is considered basically anything that's like above 1. So anything above 1 is considered a large value of K. As we talked about, there are those sort of extremes to that. Really, really large values of K and really, really small values of K in between. We talked about a couple different types of K, I believe. Kc, which is how we do it with concentrations. We also talked about Kp, which we do when we are dealing with pressures. Remember that typically speaking, the standardized unit for pressure is atmospheres. So again, in a lot of these sort of calculations, even if they may give you values of pressures in different units and even ask for the answer in different units of pressure, a lot of times in equilibrium sort of calculations, you got to kind of get it to atmospheres, do the calculation, and then convert it at the end. So that's sort of the proper way that you need to do that. There is a relationship between these two, which is the Kp is equal to Kc, a little RT delta N action. That's our pressure equilibrium constant. That's our concentration equilibrium constant. That's the R, not the one you use on the quiz there, but hopefully the one that you use there for the ideal gas law. That's our temperature in Kelvin. And as we talked about, that is the delta N, which is the change in the number of moles of gas. So that, again, is the moles of your product minus the moles of your reactants that are gases. And as we talked about, that's really important to make sure that if it is negative, you keep it, because mathematically, obviously, you will get a different answer if you don't keep the negative part of it. So make sure that you do always the products minus reactants there. Towards the end there, we got into talking about ways that we can manipulate equations and really the effect that it has on the equilibrium constant. So a couple of ways that we talked about is we have a reaction such as this, and we have our equilibrium constant, which is our C and our D divided by our A and our B. If we were to reverse that reaction, that would give us this, which is our A and our B, and that is our C and our D. So when we do reverse a reaction, as we go from here to here, we basically take 1 over the K value. So again, we don't change the sign or anything like that. It's 1 over the K value. Also, if we need to multiply by a common number, . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . again, that would give us a K value for this one of C squared D squared divided by A squared and B squared. So basically, as we went from our original to here, we basically squared the K value. And that's because we basically multiplied by 2. As you go the other way, if you had to divide by the common number, again, you would actually take the square root. So if you were kind of going this way, you would take the square root of K1. If you went divided by 3, you would take the cube root of K1. So again, that's also different. Lastly, the other thing that's a very common mistake that people make when they are adding equations together and they're looking for the K value for the overall equation is when we do add equations, we actually multiply the K value. So again, that's something that's different than, say, delta H. So again, if we have this equation, and this is K1 and this is K2, these guys will cancel, giving us our overall equation here. And our K value for this one would be these two K values, again, multiplied by each other, not added, which again is a common sort of error that people make. Any questions on that stuff that we talked about last time? The key with that is just to keep it simple. If you are adding equations, to sort of build an overall equation, you just gotta keep track of what you did to everybody, and then obviously do the math correctly when you put them together. So a couple final thoughts here on this part of it. As we've been talking about, the concentration of reactive species are usually expressed in molarity or atmospheres. Concentrations, again, of solids or liquids are not included in the equilibrium constant. Again, solids and liquids really don't participate in the equilibrium, so we do not put those guys in. That, again, basically means, as we talked about, you're left with two things that go in, which are basically these two things. Anything that has aqueous or gas next to it will be included in the equilibrium constant. As I said before, no units, just a number. And again, it is specific for that particular temperature and exactly how the reaction is written. And these are just, again, a couple things we just talked about there in terms of manipulating equations. Again, if you need to multiply by that number, we're going to take it to whatever that number is. And if we're going to divide by a number, we're going to take the root to whatever we divided by in terms of our K value. Now, again, the thing that's really hard for people is it will always have the same value K, regardless of how much you start with. So again, that simple example that we talked about the other day where, you know, if you want a K value of this 2, there are multiple sort of ratios that will get you to 2, right? And that's the same idea here. Although you may not be starting with the same amounts in every experiment, when you get to that final ratio, the proportion of products to reactants will always end up being basically the same number. So let's talk about another letter here. Not too long, we'll talk about this guy, but Q was referred to as the reaction quotient. And when we talk about Q is calculated the same as K. So when you calculate Q, it is the concentration of your products. You still use your coefficients as the exponents divided by the concentration of your reactants. So Q is essentially calculated, not really essentially, but is calculated identically to how you calculate K. So you may be asking, what do we need Q for? Well, it's a different letter, so it makes us happier that way. But the real reason we use Q is typically used in a couple of situations, as we will see through this chapter. One situation is just what I call sort of a just flat out Q type question. And in those type of questions, what you're trying to determine is a couple of things. You're trying to determine, is your reaction at equilibrium? And that may be a result of your given initial concentrations, or you're not sure if they're equilibrium concentrations. You just sort of have the concentrations of everybody given to you. So a lot of times we will use Q when we're given initial concentrations to help us first determine whether or not the system is at equilibrium. And if the system is not at equilibrium, we could actually use the value of Q to help us determine which way it needs to go to actually reach equilibrium. So do we need to make more products to get to equilibrium? Do we need to make more reactants to get to equilibrium? So Q is sort of a twofold sort of calculation that you do, is calculated the same as the equilibrium constant. But it gives you that information. It really tells you whether or not you are at equilibrium, and sometimes more importantly, which way you need to go to reach equilibrium. So if you calculate Q and it's greater than the Kc value, it means that you are not at equilibrium. And in order to reach equilibrium, it actually needs to make more reactants. So if you put Q like it is here, all on the left-hand side and K on the right-hand side, it goes opposite of where that sign is pointing to. So it's like going towards reactants to products, right? It has head in that direction. If you calculate Q and it is the same value as the K value, then your system is at equilibrium. Doesn't really need to go either way. It's going to basically be happy right there. It's at equilibrium. If you calculate Q and it's less than K, it will tell you that, again, your system is not at equilibrium. And in this particular case, in order to reach equilibrium, you got to head in that direction towards the product side to make more products to reach equilibrium. Now, there's a couple of things here. Again, Q, you still use those coefficients as the exponents. And clearly, the only way that you could calculate Q is you would need all the concentrations given to you, right? So you clearly cannot calculate Q if you're not given all the concentrations. So that's one big hint of, I probably should calculate Q here since I'm given like all the concentrations. So that's a way that you know you should sort of calculate. Another place that we will see Q is a little bit later on when we talk about sort of solving equilibrium problems. And in some of those cases, in addition to solving the equilibrium problem, the first thing that you really should do is sort of calculate Q so you know sort of which way the reaction is sort of proceeding to do that. So there is sort of, like I said, kind of two types of situations that you use Q. A lot of times it will just be a straight question like that. Is this system at equilibrium? And if not, which way it needs to go to reach equilibrium? The second sort of application of Q is in this sort of chapter, as you're solving equilibrium problems, you may have to actually calculate beforehand. So again, you do obviously need everybody's concentration to do so, or there's no possible way to calculate Q. And usually in those problems, you will have obviously the K value given to you. So you have something obviously to compare it to when you want to calculate Q. Any questions on that there? All right, so why don't you try one here? Let's start a reaction. We got 0.249 moles of N2, 3.21 times 10 to the minus 2 moles of H2. And we got some NH3 happening there. If the K value is 1.2, is the system at equilibrium? And if not, which way does it need to go to reach equilibrium? Okay, let's take a look. So this again is a situation where we are given the concentrations here. Not really, but we're given the moles and the liters. So we can get to the concentrations of everybody here, the N2, the H2, and the NH3 in this case. So this is a situation where we can calculate Q because we can get the concentrations of everybody. Once again, Q is calculated the exact same way as you would write the equilibrium constant. So in this case, we would again take our products, which is the concentration of NH3, and just like we did with the equilibrium constant, we will square it because of the coefficient that is present. We will then divide it by the concentration of our N2 and the concentration of our H2. And once again, here we will need to take it to the third power there because of the coefficient. So as I mentioned, Q is set up exactly the same way as the equilibrium constant. The only difference is you just don't know if you're at equilibrium. So in order to put obviously our values into here, we do need to convert it into molarity. And here we have moles and liters separate. So that might be something we would want to do. We're going to take the concentration of N2, and that would be our moles of it, which is 0.249 moles divided by our liters, 3.5 liters. And that's going to get us 0.249 divided by 3.5. 0.0711, we'll call it molar. We'll also do the same thing for our H2. We'll take the moles, which is 3.21 times 10 to the minus 2, also divided by 3.5 liters. Gonna go 3.21, make sure you use your exponent button, minus 2 divided by 3.5, and we'll go with 0.00917. And lastly, NH3, I think we got going on there. So we'll do it down here. NH3 will be our 6.42 times 10 to the minus 4 moles divided by 3.5 liters. And that's going to give us 0.000183 molar. So we have everything that we need to go into our expression. So we're going to put it in there. So our NH3 is 0.000183 squared divided by our N2, which is 0.0711, and our H2 0.00917. And once again, here we do need to cube that guy. Any questions on that so far? All right, so we put this into our trusty calculator here, see what it says. We're going to take the top number there, going to square it. I'm going to divide it by 0.0711. It's going to hit equals, going to divide it by 0.00917 to the third power. And go with 0.611 as our Q value. Now, yeah. It does, and so it's very similar to pretty much the equilibrium constant, so it typically will not have units like it. Yeah. Because really you kind of use it to compare to the equilibrium constant, so you're just comparing numbers to numbers. Other questions? In this case, we do want to compare, so we have our Q value, we have our KC value that was given to us in the problem of 1.2. In this case, our Q and KC, our Q is greater than or less than that our KC. So the first thing that this tells us is this system at equilibrium? The system is not at equilibrium, again, because they do not equal each other. So it's only at equilibrium if both of those values do equal each other. In this case, we need to go which way? Do we need more reactants or products in this case? We do need more products. And again, I personally just remember it pointing opposite of where that's going. That way is where we need to go towards the products, provided obviously you put Q on the left and K on the right. And we would need to head towards the product side there to make more products to reach equilibrium. Any questions on that one there? So this is what I would classify as just a straightforward Q type question. And those are usually the kind of couple of things that you're sort of would use Q for. And again, as I mentioned, we'll kind of see it here in a few examples down the road, where another place where it'd be a good idea to calculate. Any questions on Q? All right. Now that we talked about Q, let's get back to the important letter, which is K. I feel lonely. We missed it for a while. So now let's talk about really the main calculation here of the season. And this is actually solving equilibrium constant type problems. We will do a version of this calculation many different times, many different ways. You almost can't go wrong to do this calculation in a lot of cases, but there are places where you shouldn't, but most of the time you will do this. So when we solve equilibrium constant problems, we usually want to make sure that for sure when we do this type of calculation, that the concentrations and molarity are, again, you can also do this calculation in pressure as well. So as I mentioned earlier, you want to make sure, definitely when you go into this calculation we're going to talk about here, that if you are doing it with pressure, that they are in atmospheres. So make sure that they have to be in that. So we solve these problems by really solving for an unknown value. And the unknown value is really the change that is occurring in this reaction. And the way that we solve these problems is everybody's favorite thing, which is ice. I won't finish the song. So that is ice, which stands for initial change and equilibrium. Now, you might have used ice tables. Ice table, I guess I write table next to it. Ice tables is what we're going to use. Now, you might have used ice tables when you did limiting reagents, a little stoichiometry. Anybody use ice tables when they did that? No, nobody teaches you that. They should, because, you know, you come here, then that's like the calculation you're using. By the way, it also makes the stoichiometry calculation way easier. But they really should teach you that, but they don't. Unless you took me, then I would have taught you that, but you didn't take me. That's probably because I didn't teach it, so sorry. So these are it's very valuable sort of calculation. So just so you know, you could, if you want to do a stoichiometry calculation in the future, you could actually do it like this as well. So when we have a reaction, let's just make one up here. Let's say we have A plus B goes to 2C or something like that. Try that. And in this particular case, let's just say that we have an initial concentration of A of, say, I don't know, we'll go with 2 molar. And we have initial concentration of B here of, we'll go with 3 molar. Why not? All right, so we have these concentrations. This is really all that's given to us. We may also be given an equilibrium constant value, which is very commonly given. So let's just say the K value here is 12 or something. All right, so in order to solve this, what we would be looking for is the equilibrium concentrations of everybody at equilibrium when they reach it there. So these are assumed to be initial concentrations, and you probably can make a pretty safe assumption that they are initial concentrations in most of these problems that you're given, even though a lot of times they won't just flat out say it. They won't say it, they're initial. They'll just give you some concentration. So you could think about them as initial concentrations. So when we go to our ice table, we're going to start with I, which is initial. So basically we would just fill in what they gave us, which is 2 molar in this case. And that would be our 3 molar. And now we're not initially given any information about our products, right? So in this type of situation, it's pretty safe to assume that you don't have any products to begin with. So it's pretty safe to assume that this is going to be a 0 here for our products. Again, they would sort of give you that concentration if they wanted you to have it. So the first question is here, would I be able to, for example, calculate Q if I wanted to in this case? Could I calculate Q in this case? I could not, because they didn't give us the concentration of C to begin with. So we really can't calculate Q. So this would be a situation where you wouldn't want to do it. If you were given a problem like this where they did give you everybody's concentrations, then you might want to calculate Q. But obviously we couldn't here. Now, the really important part of this table is the change part. And the change part is represented by a letter, and everybody chose X, so we'll use X. So X is the letter that we use to represent the change that's occurring in this particular case. Now, when we look at our initial line and we do not have products at this point, it is also probably a pretty safe assumption that this reaction is heading in which direction? Yeah, it's heading towards the products, right? So we really don't have products. All we have is reactants, which means that's going to really kick off the forward direction here in this reaction, right? It's going to head towards the products. That means as this reaction takes place, the amount of reactants, should they be less than what we started with or more than what we started with? Should they be decreasing or increasing the amount of reactants? Should be decreasing, right? Because you need the reactants to make the products. And by that same token, we should expect that the product should be increasing with time. And we represent sort of decreasing and increasing in terms of the change as minuses and pluses. So what we would want to do is on our reactant side, where we would assume that they should be decreasing, this would be minus X, this would be minus X. And on our product side, this would actually be plus 2X. Now you can see I put a 2 at the end there, and that is because there is a 2 here, right? I didn't put any numbers on the other ones because the numbers of the coefficients here are 1s, yeah? Now, if they were not 1s, you need to put numbers. So the important part of the change is, in addition to the minuses and the pluses, is you do need to incorporate the coefficient into those x's. And what that does for you is the stoichiometry part that we talked about, which is why you could use this in that calculation. It does the mole-to-mole relationship for you in the calculation, which if you do not do that, you will have the wrong mole-to-mole relationship, you'll have the wrong stoichiometry, and you will get the wrong answer. So you do need to, in the change part, make sure that you take into account, again, those coefficients. Otherwise, at the end, you will not be so good. Yeah. Any questions on that so far? At this point, we're just going to finish our table by going to equilibrium. And we're just going to drag everybody down. So 2 minus x, 3 minus x, and 2x, basically. Now, what we do with it at this point is we're going to put it into the equilibrium expression. So we could write the equilibrium expression for my made-up example here. And in my made-up example, this would be the concentration of C, and I would have to square it, right? Divided by the concentration of A times the concentration of B. Also, we would need to take into account our coefficients there as well as we do it. And this would equal 12, right? So at this point, what we would do is we would take everybody from our equilibrium line, everybody here from our equilibrium line, and basically put it into our equilibrium expression, and we would solve for x. So we would take our values there, and we will take our 2x, which would be squared, divided by our 2.0 minus x times our 3.0 minus x, and that would equal 12. At this point, the goal here is to solve for x. Yeah. This is where the fun math comes into play. Yeah. So a lot of math, I believe you got to do a little foiling method there, or whatever they call that, cooking Thanksgiving dinner or whatever, maybe there. A little in and out action there in case you want hamburgers instead, right? So you got to go in and out on that. You also need to do a little squaring action of that, right? I need to square the x, right? How about the 2? Yeah, most people miss the 2, by the way. Yeah, so you want to make sure that you square the 2 there as well. Very common mistakes that most people make. All right, so you can go through all that. Or maybe just move on to the next question, whatever it may be. But you might go through all that and finish it. So after you factor all that out, we do need to solve for x. And there's a few different ways that you could solve for x, which we will go through in some different examples. But probably the most complicated way that we would solve for x is to use the quadratic formula. So the quadratic formula is x is equal to, I'm going to try to remember, minus b plus or minus a little square root action of b squared minus 4ac divided by 2a. You agree? That's good. I mean, it's been a while since I've been taking math, I walk by the math building, but it's all right. Actually, I don't know. It's just, and that is based off of this formula here, which is ax squared, right? Plus bx plus c is equal to 0, right? And that's where we get the a, b, and c action. So when you do all this sort of math over here, you do a lot of times need to combine it into a little quadratic type of equation there so that you could use the quadratic formula to solve it. By the way, since we have the quadratic formula up there, how many answers do you get out of the quadratic formula? You do get 2 answers, so you will get 2 x values, right? And in this case, what will happen is one of the x values will not make sense, right? And what I mean by not making sense is what we will do with these x values, if you get it through the quadratic formula or you get it through some other type of calculation that we'll talk about. But once you get the x value, that x value is every x value that is in your table here, right? So what we typically would do at that point is go back to our table to the equilibrium line and basically put in our X value. And what that will actually give you now is a value for each of those guys when they reach equilibrium. So that is sort of the goal of these ICE tables and how you solve equilibrium problems. We use these ICE tables and we solve for X, which is really the change that's going on. Once we get the X value, we could then insert it into the equilibrium line, and that will give us our value for the equilibrium concentrations of each of these. You could also do this with pressure, as I mentioned before. So instead of concentrations into this table, you could do ATMs into this table. You probably would not be using a Kc value, but maybe a Kp value in that case, right? So you could do the exact sort of same calculation doing that. Speaking about a couple of things here to finish up today with is, we just talked about, you do get two values if you do have to go down the quadratic route there to solve it. And what I mean by one of the values will not make sense is when you go to put it back into the equilibrium line, one of these guys will yield you a negative number, and you clearly cannot have a negative concentration or a negative pressure. So that will be the one that you would not use. Now, sometimes people get confused on that, and there are really three combinations of values you could get. You could get a positive and a negative number, right? Which in that case, probably the negative number might be the one that's wrong. You could get two positive numbers, right? And you could actually get two negative numbers as well. So your possibilities of when you go into the quadratic is any of those threes, but what you're looking for is when you put it back into the equilibrium line, if you do get a negative number, then that is not the correct value to use. You would then want to use the other value. So that is what you're looking for in that situation. Now, to finish up on this conversation, since it's fresh in our head about Q, we would want to, in a equilibrium problem like this, calculate Q if we were given all of the concentrations, right? And the thing that would be affected by that in this table would be which line would be affected. Let's say you calculate Q and it says to reach equilibrium, you're probably not at equilibrium, otherwise it wouldn't be much of a problem for you to do. But to reach equilibrium, you need to actually make more reactants. What would change in this table? Well, the thing that would change is the change part. Yes. And in this case, we're actually saying, I know I got a whole semester. Let's get it. I got bound to. So in this case, what we're saying by this table that we originally did is we're saying that this reaction is heading to the product side to reach equilibrium, right? That's why our minuses are on the reactant side and our positives there are on the product side. If we happen to calculate Q in a situation, but it's actually going in the other direction, that would mean that these guys should actually be positives, right? And this guy here should be negative as it's going in the opposite direction. So that's why it's important sometimes, and that's the second place where Q could come into play, is a equilibrium type of calculation like this, where they give you the concentrations of everybody. And in a lot of cases, you can almost 99% of the time just autopilot it. It's going to the product side, but there could be a situation where it could be going the other way, and calculating Q could help you either reaffirm that it's going to the product side or make a correction if you needed to go the other way. Any questions on that? All right, so that was a nice little put in the pool today. Yes. On Thursday, we'll dive in head first, deep end. All right.